for many decades, actually looked to find short flashes of radio light. But the problem compared to gamma rays, where we have gamma ray bursts happening a couple times a week over the whole sky, at least the ones that we can observe, the problem in radio is having sufficient sensitivity and field of view is quite challenging. So a telescope like the Parkes telescope, which is the current record holder in terms of finding large numbers of fast radio bursts, has found a couple dozen events so far. That telescope has sufficient sensitivity to detect this fast radio burst phenomena, which I'll describe in a few minutes, but it has an absolutely tiny field of view compared to that of an all-sky monitor. In fact, the Parkes telescope, even though it has quite a large field of view compared to your typical radio telescope, is still much, much smaller than a square degree. That means that even Parkes, which is very good at finding fast radio bursts, it still takes Parkes 10 days of continuous observing to find roughly one fast radio burst. So we're really not in the regime where we can do a radio all-sky monitor yet. The other challenge compared to high energies, X-rays and gamma rays, is the fact that radio signals are unavoidably corrupted or influenced by their propagation towards us. So the equation that you see at the top is trying to show you that the emitted signal, this S of t there, that comes from an astrophysical object is quite different than what we actually observe at a radio telescope. Because this signal is modulated by refractive and diffractive scintillation. It's passing through a transfer function describing the dispersive properties of the interstellar medium, Faraday rotation due to the line of sight magnetic field, scattering due to inhomogeneities along the line of sight due to multipath propagation. And thus what we detect has been corrupted by all of these effects. And on the right, for instance, this is showing you something that you should, if you're going to take anything away from this talk, understand very well, is that short duration radio signals are dispersed by the intervening ionized material. So what you're seeing as a function of frequency at time, some particular pulse will arrive later at lower frequencies. So certainly keep that in mind. That's critical to understanding most of the talk. So this is a hindrance. It makes it difficult to detect these types of signals, but it can also be a help because it helps us differentiate short duration radio flashes that are astrophysical in nature from those that are man-made, from radio frequency interference. And it also allows us to, in some cases, learn more about what's going on along the line of sight and to use these effects as a proxy for distance as well, which is another crucial thing to understand. So 10 years ago, this conference is to a certain degree celebrating 50 years of neutron stars, but we're also celebrating about 10 years of fast radio bursts because 10 years ago, using the Parkes radio telescope, Dunk Lorimer and one of his students and a number of other collaborators, they found what is now colloquially termed the Lorimer Burst. And what is the Lorimer Burst? Well, the Lorimer Burst was a bright, non-repeating, single flash of radio light. It was detected off-axis, but it was still very bright. The inferred flux density is on the order of tens of Janskys. And as I just told you, the signal, because of propagation through the ionized material between us and the source, it is arriving later at lower frequencies. So in this frequency time diagram, again, the signal is arriving later at lower frequencies. And if you correct for this effect, if you, what we call de-disperse the data, so if you can imagine shifting all of these frequency channels in time such that they all line up at the same time, then that pulse that you see in the inset, that would be the pulse if you add all of the frequencies together. So this was interesting because this was a very bright flash of radio light. Given the field of view, which again is tiny for a radio telescope, the implied rate is hundreds of, or if not thousands of these events per sky per day. So if you had a radio telescope of comparable sensitivity to Parkes, and if you were looking at the whole sky, we would have found many fast radio bursts already during the time of this talk. And I told you that dispersion allows us to figure out kind of the distance to a source. So the amount of delay as a function of frequency is a proxy for distance, but you need another input, and that's of course how the material along the line of sight is distributed. So these two plots here are showing ISO contours, so constant dispersion measure, the amount of column density, let's say, along the line of sight, either looking down on our galactic plane in the left-hand side here, or looking on the right across the galactic plane. And you can see, of course, if you look within the plane of our galaxy, you build up material very quickly. There's lots of stuff to look through. And if you look off the galactic plane, then you don't build up a column density of dispersive material very quickly. So using a model like this, and the measured dispersive delay, you can figure out the distance to a source in a model-dependent way, of course. And what was interesting about the Lorimer burst was, well, we can figure out for this particular line of sight, which happens to be towards the Large Magellanic Cloud, we can figure out how much dispersive delay we would expect from all of the material from the Milky Way galaxy. And the amount of dispersive delay across the whole band is given by this green bar here. And as you can see, the amount of dispersive delay that was observed, much, much larger. So what Dunk Lorimer and his co-authors concluded was that this extra dispersive delay must come from another column of ionized material, from the intergalactic medium, and potentially from the host galaxy of this source. So they concluded that this must be an extragalactic radio signal that had traveled through the ionized material of its host galaxy and through the ionized intergalactic medium. So this is very interesting because not only was this source bright if it was at that kind of distance, and we're talking about a distance of 1.5 gigaparsecs or so, it would have to be quite unlike radio signals that we see from typical pulsars. And this means that we're then probing a new parameter space of radio transients. This is a diagram that was made by Evan Keane, but it's based off work that Jim Cordes pioneered in the early 2000s. Essentially what it's showing are various different types of radio transients as a function of their duration. The x-axis is basically the duration of the radio transient, and then its luminosity on the y-axis. And pulsars, they inhabit this area around a few milliseconds or so with typical luminosities of a few Janskis per kiloparsec squared. We have the crab giant pulses over there at much shorter durations and much higher luminosities. But the Lorimer burst, as you can see, is many orders of magnitude higher in luminosity if the inferred distance is correct. And of course, as many of you know, there was a great deal of controversy about the extragalactic interpretation because that was based purely off this unexpectedly large dispersive delay. So that's really interesting. Apparently we have this new type of phenomena, this fast radio burst phenomenon. They appear to be coming from extragalactic space. They are very, very bright, short duration. Many, many models have been published speculating on what these sources might be. There have been galactic models in the early days trying to interpret these things as pulsars or magnetars, perhaps behind some extra cloud of ionized material that we had not previously known about. But there's also many extragalactic models, some of which are very exotic in variety, even evaporating black holes. So what are these sources? We don't know yet, but this is one of the things I'm going to try and touch on in the talk. And let's assume that they are real and that they're extragalactic. What good are they to us? What can they teach us? Well, they're certainly, if they are extragalactic, they're certainly the sites of extreme energy densities. So they're, I think, important in their own right to understand what kind of extreme astrophysical environment can produce such bursts. They may be pointing us to a new type of astrophysical object, although for the purposes of this conference, hopefully they're pointing us towards neutron stars, otherwise I'm speaking at the wrong conference. But regardless of their nature, if we can understand some of the complicating factors at the site of production, the influence of the host galaxy and other messiness, potentially they could be very interesting probes of intergalactic space, because again, the signal that we're observing has been modulated in various ways because of its propagation through the ionized intergalactic material. So we could use these sources potentially to probe the densities and the magnetic fields of intergalactic space in a way that's not possible otherwise. So just to give some context to what I'm going to be talking about here, basically the history of the field in the last 10 years or so is that we started with this Lorimer burst, the first, let's call it fast radio burst. There were actually a number of interesting papers written in the last few decades that in retrospect may have actually been detecting this phenomena as well. But between the Lorimer burst and really the field getting going, amount of time passed in which there was a lot of let's say, controversy about whether the sources were even astrophysical in nature. And as many of you know, for instance, at Parkes they discovered a somewhat similar phenomena that was coming from opening the microwave too early during lunchtime. And these kinds of things really, stopped the field from gaining a large amount of momentum in the early days. But really, with the discovery of a whole population in 2013 by Thornton et al., they found 4 fast radio bursts in a survey with the Parkes telescope. I think a lot of people really started to believe that this must be an astrophysical phenomena. And the discovery of a fast radio burst with the Arecibo telescope, the first telescope other than Parkes, really started to convince people that this must be a genuine astrophysical phenomenon. And it's this particular burst that I'm going to be talking about in most detail during my talk. So really in the last few years or so, since 2015, there's been an explosion of papers, interesting results that are starting to give us the important clues that we need to figure out what this phenomena actually is. This includes things such as the first detection of a burst in real time. So people have been beefing up the amount of computer power that we have at each radio telescope to start detecting this phenomena in real time, because if you can detect it in real time, you can start triggering other telescopes. You can take data of higher quality. You can store, for instance, the full Stokes parameters of the signal. So this first real-time burst also detected circular polarization in the burst, which is interesting. Later that year, there was a burst detected with a very large rotation measure, which is essentially measuring the line of sight magnetic field, and it showed that whatever the site of production was, it must be strongly magnetized, so that was also very physically diagnostic. Another event was found only about a year ago that was equally as bright to the Lorimer Burst, suggesting that actually we don't need particularly large radio telescopes. As long as we have a very large field of view, the luminosity distribution may be such that we can actually find a lot of these even with small telescopes. But most of the talk I'm going to be talking about these papers in which the Arecibo fast radio burst that we discovered a few years ago was found to be repeating. So going back to the source, we were able to find bursts at the same dispersion measure and thus the same distance and the consistent sky location. And because the source was repeating, this allowed us to sit on the source for a very long time with every telescope that you can imagine and to start learning more about its nature. And that's what I'm going to talk about in more detail in this talk. So we have this fast radio burst whose name is FRB 121102 because the first burst that was detected on the 2nd of November 2012. And again, it was found with the Arecibo radio telescope in Puerto Rico. And Arecibo's most important operational parameter, I think, in this respect is the fact that it's a huge radio dish. It's 300 meters across. And compared to the Parkes telescope, even though we're sacrificing quite an enormous amount of field of view, the sensitivity is over an order of magnitude larger than Parkes. So it's possible to see much weaker astrophysical signals than with the Parkes telescope. The signal was found in the PALFA survey. This is a survey for radio pulsars in the galactic plane. It's using a 7-beam receiver system, which is basically a clone of the Parkes multi-beam system. And it's one of the deepest surveys before the square kilometer array will come online. And what I think is kind of funny about this is if you make a diagram looking down on the galactic plane, you can see these black lines showing the various spiral arms of the Milky Way. All of these blue dots are showing you discoveries of pulsars and rotating radio transients from the survey. And you can see that Arecibo can see in two small quadrants of the galactic plane. This is because the telescope, the dish cannot move, so it's a pseudo-transit instrument. And you can see that in the inner galaxy, there have been many pulsars that have been discovered, even out to the edge of the galaxy. But in the galactic anticenter region, where there's not that much galaxy to look through anymore, there have been very few discoveries. And you might ask yourself, well, why are you spending time finding a small handful of pulsars in the galactic anticenter? And I was kind of wondering that as well. But the important thing is these data are taken commensally. So there are people using the data for other scientific endeavors, such as looking for extragalactic sources and galactic hydrogen absorption. And even though there have been only a few pulsar discoveries in that direction, the data is coming for free. But quite fortunately, that commensal data is the data in which this fast radio burst was found. So looking in this anticenter region turned out to be useful because that large on-sky time was the reason why we were able to find this burst. So again, this is the burst itself. This is found about three years ago by Laura Spittler, searching through the Arecibo data, specifically looking for fast radio bursts. And this is what she found. This is, again, as a function of frequency and time. The signal has not been de-dispersed, so this sweep that you see is still due to the ionized material between us and the source. If you sum all of the frequency channels together with the appropriate correction, then that's the burst. Not nearly as bright as the Lorimer burst, as you can see. But what was particularly strange about this, and what had a number of us very worried, is if you look at the spectrum of this of this burst is really quite strange. It's obviously becoming much brighter towards higher frequencies. It appears to have an inverted spectrum, actually with a spectral index of +7 or so. And that doesn't seem very astrophysical. That was a little bit strange. In fact, our conclusion at the time is that we must have seen the burst through a side lobe of the telescope where the instrumental response of the telescope was the main driving factor for this spectrum. So the source was in the galactic anticenter. Of course, you know, the first thing you do when you find a source that has a large dispersion measure is you try and figure out whether it could still be consistent with the galactic dispersive column. That's the position of the burst there. There was nothing obviously along that line of sight that could contribute to the large dispersive delay here. And in fact, the dispersion delay for this burst is 3 times larger than what could be explained by our galaxy, depending on, you know, your exact model for our galaxy. But still, it seemed like it must be extragalactic. Now, where the story became much more interesting, however, was when we realized, well, we should go back to the source and we should establish that it's not producing repeat bursts. Even though it's well known within the field that fast radio bursts don't repeat, it's still due diligence to go back and to establish that fact empirically. So we were quite surprised, actually, when we went back and with a short campaign, a campaign of only about 10 hours or so, we were able to detect 10 additional bursts at consistent sky positions. They're all coming from the same direction, and they all had the same dispersion measure. So these are the next 10 bursts. The original burst is at the top there. Here, the dispersive delay has been corrected. So these frequency time diagrams, that dispersive delay has been taken out to try and make you know, this straight as a function of frequency. As you can see, some of the new bursts are much brighter than the original one that was discovered. And also, quite importantly, and I'll come back to this later in the talk, the spectra are highly variable. Some of these bursts, well, the last 6 or so were detected in a time window of only about 10 minutes. And sometimes we're seeing apparent spectra of, you know, -7 and sometimes +10 within a few minutes of each other. So the spectrum is all over the map, and I'll discuss that a little bit later as well. But the most important thing is simply the fact that it's repeating. And this was the first time that we had seen a repeating fast radio burst. And this is a very easy paper to write. You know, what is the consequence of the fact that it repeats? Well, quite simply, the consequence is that the origin of the burst cannot be a one-time only explosion, as was previously popular for FRBs in general. But at least for this particular fast radio burst source, which of course could be different in nature than the other sources, for this particular source at least, whatever is producing the bursts has to be able to survive, you know, the production of the bursts themselves. It has to be able to live long enough to produce multiple bursts. So this starts to push more towards models that invoke neutron stars, some kind of pulsar on steroids kind of model. Of course, this also raises the question, you know, if repeat bursts have not been seen from the other fast radio bursts, could it be that we're already seeing multiple populations? And that could well be. It could be that there are fast radio bursts which can repeat that are non-cataclysmic in nature, and it could be that the rest of the population that we've seen thus far could still have a cataclysmic origin. Now, there have been very deep follow-ups of a number of the park's FRBs for tens of hours, in some cases even a couple hundred hours or so. But, well, if you want to discuss this in more detail, I'll take questions on this. There are still ways in which it's possible for these sources to repeat as well. It's just that we have not observed them to do so. And of course, if you look at the archive and you ask the question how many types of fast radio bursts are, there must be at least 40 or so, given all the papers out there. So Arecibo has this multi-beam receiver. This is what it looks like. And the problem is this multi-beam receiver is nice for increasing the field of view, but in terms of localizing the source, it's still quite poor, even though Arecibo is quite large. So all of these different circles, these are different areas on the sky where the main lobe of the telescope was pointed in our confirmation or in our follow-up campaign. And the circles that are marked with numbers there, those are where we found bursts. So the first burst was found in that circle with the 1 in the middle. Ironically, the first burst was indeed found in the side lobe of the telescope because the rest of the bursts that we found were somewhat off from that position, but consistent with the position that overlaps between those other two circles. So we're starting to narrow down the position of the source a little bit, but each one of these circles is 3 arc minutes across, and 3 arc minutes just does not cut it for multi-wavelength follow-up. So I'm going to tell you about 3 papers in which we've managed to localize the source and establish its extragalactic origin. These are papers that came out in January, all on the same day. So first, tell you a little bit about how the source was localized. And again, this is critical for assessing its nature. And just to motivate why it's critical, the Arecibo beam is quite small. 3 arc minutes is fairly small for a radio telescope, but it's not an interferometer. And if you do this toy comparison of sticking the Hubble deep field within that field of view, that's how large it is, roughly speaking. So if you ask yourself the question, is this source extragalactic? And if so, which of the galaxies is producing the burst? Well, you have a big problem because there's a lot of galaxies within 3 arc minutes. Now, if you can get localization with an interferometer like the VLA, where the dishes are spread over tens of kilometers, then you can really unambiguously figure out which galaxy produced the source. That was the game that we were trying to play here. So this was quite a challenging campaign, both technically and in terms of patience. Technically challenging because you need to sample at a much higher rate than typically one does with a radio interferometer. You need to sample at milliseconds instead of seconds. And this is a radio image of this field taken by summing many tens of hours of VLA data. So this is one of the deepest images I think the EVLA has ever made. And in this map, you can see a couple radio galaxies, these very bright sources. You can see the positions of the Arecibo beams in which we had found radio bursts, and you can see a number of radio sources in there. Now, this is an image made by sampling the data at tens of seconds, and this is a continuum image. We still have no idea if any of these sources has anything to do with this source of fast radio burst. But by dumping the correlator at 5 millisecond time resolution, Casey Law and Shamit Chatterjee were able to localize one of these bursts. So after many tens of hours of observing in which nothing was seen, no bursts from the source were seen for many tens of hours, the source became quite active last fall in September or so. And this is one of the bursts that was detected. And this image now, the reason you only see this one source is because this is a snapshot of only 5 milliseconds. So it's a 5 millisecond snapshot of data. And in those 5 milliseconds, there's a bright burst right there. Now, the star pattern, this is just the response of the telescope, this Y shape of the VLA, the fact that the UV coverage during 5 milliseconds is quite limited. And there it is. Source is localized, and it's localized to less than an arc second. So once you deconvolve, that's what the source looks like. And if you look at it in the frequency time domain, you see that this source nicely follows exactly the dispersive sweep you would expect, the same dispersion measure for this source as all of the other bursts that we've seen. So this really nails the association with the previously observed bursts unambiguously. And what's there? Well, now we can draw a box around the position of where the burst came from, and we can see what else is there. We see that the burst is associated with a persistent radio source. So we've moved back to this continuum radio map now. So that's the radio source there. And in very deep Keck observations, there's also a very, very faint optical smudge there. Not so obvious a priori whether it's a star or a galaxy, because it almost looks like a point source, ever so slightly extended. And I would just like to emphasize that this is a direct localization. The burst was observed in real time with an interferometer, and its position was determined to sub-arc second precision. The other game that you can try and play is you can look after a fast radio burst has happened to see if there's some kind of afterglow. Of course, this has been enormously profitable in the gamma ray burst world. But this is a direct localization, and it doesn't suffer from the same kind of statistical problems that you have with associating different events. How am I doing for time? 7 minutes. Okay. I'm going to have to be a bit faster. Okay. So we have this sub-arc second localization. What's the next thing we want to do? Well, we actually want to determine the position even more precisely. We want to do much better than just arc second precision. And the reason we want to zoom in further is we want to see, do these bursts come exactly from that position of that persistent radio source, really exactly? If so, we want to start understanding their physical relation. And we also want to know, do the bursts come from, let's say that optical source is a host galaxy, do the bursts come from the center of that host galaxy, or do they come from the outskirts? We did this using the European VLBI network, which is a network of radio telescopes spread across the world, including also in Russia, of course, and including Arecibo as well. All of those data are correlated in Dwingelo in the Netherlands, which is a very, very small place with a lot of data coming into it. So we did joint observations using Arecibo, not only because this gives a very long baseline, a very large separation between telescopes, which gives the necessary angular resolution, but also because Arecibo provides the raw collecting area that one needs to detect weak bursts. So during this period of high activity in September of last year, we were very lucky to collect a number of bursts with the European VLBI network. This is the brightest burst as seen by Arecibo. This is an image of it. That's a dirty image, and after it's cleaned, because of the limited UV coverage, one needs to consider what the systematic error is on the positions. We also made some observations of a known pulsar to kind of quantify how the positional accuracy depends on the signal to noise of a burst. And lo and behold, we have a number of weak bursts and one very bright burst that are detected by these telescopes, and we're able to actually localize the source of the burst to be within at least 10 milliarc seconds now, from the position of this persistent radio source. And we've also established that this persistent radio source is compact. We're not even resolving it, or we're ever so slightly resolving it on VLBI length scales, and that resolved nature we think is actually due to angular broadening of the source. So the bursts are coming really from exactly the position of this persistent radio source. So there's a direct physical relationship, I would argue, between the source of the burst and the source of this persistent radio source. Now the real clincher, the last thing that you need to do is you need to figure out what that optical source is. Is it really a galaxy? And if it is a galaxy, what is its redshift? So we did this using the Gemini telescope. This is work that was led by Kees Bassa and Sriharsh Tendulkar. So starting with this Keck optical image, we know that there's this faint smudge there. It's only 25th magnitude, so that's really quite weak. It seems to be slightly extended, but only ever so slightly. It's a very wimpy source. So this means that there wasn't a great deal of enthusiasm about the prospects of getting a redshift for this source, but we were quite surprised. And the reason it turned out to actually be quite easy is because this source happens to be a dwarf galaxy in which most of light is coming through spectral lines. So this is spectrum of what we now know is the host galaxy. In the blue are the spectral lines. You can see H alpha there. You can see a number of oxygen 3 lines, H beta as well. Very weak continuum, so that means that there's actually very, very few stars in the galaxy. And most importantly, what's the redshift? Well, the redshift is 0.19, which implies a luminosity distance of about a gigaparsec or so. And now finally, not only establishes conclusively the extragalactic origin of the source, it also sets the energy scale because we now know the exact distance. And it turns out the peak luminosity of these bursts is about 10 to the 40 ergs per second or so. So this was very important because for at least this fast radio burst, we've now established conclusively, not just using the dispersion measure of the burst, but really finding the host galaxy and its redshift, that the source has to be extragalactic, and we know what distance. We can look at the position of the source compared to the core of the galaxy. This is a very, very wimpy little dwarf galaxy at a gigaparsec or so. You can see the Gemini images in various bands there. The centroids are shown by those crosses, and the position from VLBI is shown there by the other cross. So there's an offset by about 0.2 arc seconds from the center of the galaxy. So it's not right in the center of its host galaxy. And in the last few minutes, I'm going to explain, what this might be telling us. So we know that the host galaxy is a star-forming dwarf galaxy. It's about 1,000 times less massive than the Milky Way. So you can see the Milky Way there for comparison, and the host galaxy is that little green smudge there. And one of the reasons this is interesting is because such galaxies are actually known to be preferentially the hosts of long gamma ray bursts and superluminous supernovae. So it's really quite intriguing that the first fast radio burst that we've been able to localize to a host galaxy happens to be in this peculiar type of host galaxy that also hosts long gamma ray bursts and superluminous supernovae. It certainly at least gives the tantalizing prospect that maybe long gamma ray bursts and superluminous supernovae are the types of explosions that produce the progenitors, the engines that create fast radio bursts. So you could imagine, for instance, long gamma ray bursts or superluminous supernovae producing, for instance, in one of the models that's out there, some kind of millisecond magnetar, which is quite young, maybe only tens of years, and through the decay of its magnetic field is producing fast radio bursts. This is one of the possibilities that seems promising, at least. So what have we been able to do in the last few months or so? Well, quite importantly, this is work by Kees Bosse in the Netherlands. Kees got, in collaboration with Sriharsh Tendulkar at McGill, he got a nice Hubble image of the host galaxy. So this gives us better angular resolution than we were able to achieve with Gemini. So you can see in the oval here, this is the extent of the host galaxy, the very weak star formation from this very small galaxy. But we see this very, very bright knot of star formation. That's where all of those spectral lines I was showing you in the Gemini spectrum are coming from. And again, the VLBI position of the fast radio burst is shown by the little X there. We see that the fast radio burst source is associated with the star-forming region. It's ever so slightly offset from the centroid of that star-forming region, but it appears to be physically related to that star-forming region. So, of course, that's another interesting clue because it suggests that whatever the source of the burst is, it's a young object produced in a star-forming region. Unfortunately, we haven't been able to find anything in X-rays. There is no persistent X-ray source. So that's the position of the burst there, and this is a Chandra image in which there are just two little lonely photons in there during long observation. And we have simultaneous radio X-ray coverage that we were able to take with Arecibo and with XMM, which shows also at the time of the burst, at the time of the radio burst, there are no coincident X-ray bursts. But I should give one very important caveat here. The distance to the source is really quite enormous. So even in some of the plausible magnetar models, given the large distance and the size of our current X-ray satellites, you would kind of just barely maybe expect to see some of these X-ray bursts. So I don't think we're able to rule out that there is some kind of simultaneous X-ray burst here. To do that, we would need to find a similar repeating source at much, much smaller distance to be able to probe these ideas, I think. And lastly, during the VLA campaign, we also had simultaneous Arecibo coverage. So we see, in some cases, bursts at two telescopes at the same time in different observing bands. And we see sometimes that the signal is very, very broadband. So in this particular case, we are able to catch a burst from 1.2 to about 3.5 gigahertz or so. So in some cases, the bursts are very broadband. But in other cases, we see that the bursts are very, very strange in their structure. So what's shown on the left is one of the brightest bursts that we've seen with Arecibo to date. This is what we're calling weird bursts. They have a lot of structure to them. So in the top panel, that is the burst structure. So all of those bumps and whatnot are real. But the data has already been de-dispersed in this case. So you can see that there's substructure, that there's sub-pulses to the burst. And they actually are delayed with respect to each other in frequency and time. They seem to drift down to lower frequencies with time. And we don't think this is dispersion. One of my postdocs, Anne Archibald, she was kind enough to print out this particular burst in 3D with her nice 3D printer. So at coffee, if you want something to poke someone with, you can take a look at this. I think it's an easier way of visualizing this than what's shown on the screen there. And we think that this spectrotemporal behavior is going to be highly diagnostic for understanding the environment and or the emission mechanism. So in summary, this particular fast radio burst, 121102, it requires a source that can survive creating the burst because we see repeated bursts, right? It is located, we now know, unambiguously in a galaxy at 1 gigaparsec, so at a redshift of 0.19, and it's in a star-forming region, specifically in that dwarf galaxy. And this is a type of dwarf galaxy where the metallicity is very low. You can form very, very massive or very fast-rotating stars, and where you expect to see long gamma-ray bursts and superluminous supernovae. The source is consistent or coincident with a persistent radio source. I would say it's associated with a persistent radio source given the enormously tight constraint on the angular offset. This could be a nebula. Maybe Pat will jump up and say, how could it be a nebula? Because this particular source would have to be about 500,000 times brighter than the Crab Nebula, so that's challenging. Or it could be AGN-like. There are certainly models out there suggesting maybe if you had a neutron star interacting with an AGN, you could produce such electromagnetic bursts. In any case, if it is a nebula, it needs to really be quite unlike any of the pulsar wind nebulae or magnetar nebulae that we've seen in our own galaxy. The energy scale of the burst is now well established, and I think it's still possible to get this out of a neutron star. Certainly, you know, if you increase the rotation or the magnetic field or the efficiency of the radio production, then you can get the orders of magnitude that you would need. And lastly, I think, you know, the spectral temporal behavior that I just showed you is going to be really interesting, and there are ideas about how we could potentially produce this with lensing of the burst by plasma around the source, or it might be telling us something interesting about cyclotron masers being responsible for the weird spectra that we're seeing in the burst. So thank you very much.
Questions? Please.
Yeah. So we have an ongoing VLBI campaign in which for the next couple of years we're getting about 4 epochs a year in which we're going to measure the position of the source, and we can put further constraints on the proper motion. So if you think that, for instance, that the association with this host galaxy is still questionable, then you can also, from the point of view, look at the proper motion of the source and constrain its distance that way.
Sergey?
It's roughly the total number of detected bursts and how they are distributed in time, like coming in first.
Yeah, that's also a very good question. I didn't have time to get into all of the details about the source, but we now have, in a campaign of about 130 hours, we have about 132 bursts now. And many of those bursts happen within a few-week period. So there's definitely a clustering of the bursts in time, and there are periods of tens of hours where we see basically no bursts, and then periods of even an hour where we'll suddenly see 10 or 20 bursts or so. So they're definitely clustered in time.
And what is the luminosity function of the bursts?
That it's a power law. I think it's 0.7 or so. Yeah, so we're not even seeing the weakest bursts yet, even with Arecibo. So unfortunately there's only one Parkes FRB that's far enough north that it can be seen with Arecibo, but we've been following it up. So far we haven't found any bursts. The one that was found with GBT is also being followed up with Arecibo. There are plans with some of the new FRB machines, the telescopes that should find many dozens of these, like ASCAP and also CHIME in Canada. Especially CHIME in Canada is going to be a transit instrument, so it's going to see the same sky every single day, and they're going to find ones, and they will naturally see whether they're repeats or not. Now, for the ones, sorry?
Let's say if you downscale this repeating burst, obviously those are sensitive enough to see the repeating burst of this one.
Yeah, I think the very brightest ones should be visible still. Yeah, that's right. But because of the varying activity level, I would argue that we don't actually have strong constraints on the Parkes ones yet to know whether it's impossible for them to repeat. Because if the activity level is clustered in time, it becomes more and more difficult to put strong constraints on repeatability.
While the next speaker gets ready, we take another question from Ali.
What is the time average luminosity for this whole series of bursts?
That's a good question. It's quite small still. It's still much, much smaller than the persistent source by many orders of magnitude. I don't want to give a number because I need to think about it more carefully, but it's still very, very low because even in an observation where you have 2 hours, 20 bursts, this 20 bursts for about, 30 or 40 milliseconds over the course of 7,200 seconds or so. So it's very, very low still, the time averaged.
But
I think there were a couple of them in the end, so I think in total it was about 60 kiloseconds or so. So you'd have to, the prospects for going deeper are not very good, unfortunately.
There are other questions? If not, we thank again Jason. Our next speaker is Dick Manchester, who is going to talk about timing of pulsars.
So, so I'd like to tell you a bit about pulsar timing. It's obviously a key part of the science of pulsars. So I'll try to give a bit of an introduction and then go on to talk about some more recent results. So this is the observed period distribution for pulsars. There's currently about 2,600 pulsars known. Almost all of those are in the galaxy. There's 29 extragalactic pulsars, all of which are in the Magellanic Clouds. As is well known, the pulsars go into two groups, millisecond pulsars and normal pulsars. Most of the millisecond pulsars are binary, indicated by the blue colour, and many of the millisecond pulsars are in globular clusters. So I won't be talking about these source classes in this talk, but I will talk quite a bit about millisecond pulsars and normal pulsars. So this is the PP dot diagram. The lights are a bit bright to see it very well, but I think everybody's seen this before. The point here is that there's enormous diversity in the pulsar population. The millisecond pulsars live down here. Here are the normal pulsars, and up here we have the magnetars. And Sama Safihab will talk, when is it, Thursday morning, about the diversity of neutron stars, of pulsars. So there are these two basic properties, the characteristic age and the surface dipole field, which there are lines on here which you can't really see, which are lines of constant field and age. So we can measure pulsar periods to very high precision. So how do we actually do that? We first of all, when a pulsar is found, we have a basic period and usually the dispersion measure, sort of very approximate, but enough to average a certain amount of data together to form a mean pulse profile over half an hour or so. We then can cross-correlate that mean pulse profile with a standard template to give what's called the pulse time of arrival at the telescope. So that's the basic quantity of pulsar timing. And then we then measure a series of these TOAs over days and weeks and months and years. Because the Earth is a moving frame, it's rotating, it's going around the sun, we have to transfer these TOAs to an inertial frame, and we use the solar system barycenter for that. So we then compare these barycentric TOAs with predicted values from a model for the pulsar. So the model for the pulsar includes its position, its the pulse frequency. If it's a binary, it includes all the binary parameters and so on. And the differences between the observed TOAs and the model TOAs are called timing residuals. So we then fit these observed timing residuals with functions that represent the errors in the model parameters. And so this shows the types of variations that you can see with different errors. So if the pulse frequency is wrong, then there's just a linear drift in time with the TOAs. And from the gradient of that, you can correct the pulse frequency. If the frequency derivative is wrong, you get a parabola. Because of the barycentric correction, the position of the pulsar matters, and if that's incorrect, you get an annual term as the Earth moves around the Sun, and from the phase and amplitude of that you can correct the pulsar position and get very, very precise precisions. You can even measure proper motions and parallaxes. If the pulsar is binary, you get these complicated functions at the at the orbital period, which repeat at the orbital period. So by solving for all of, looking for these characteristic signatures in the timing residuals, you can improve the parameters of the pulsar. Once you've done that, if you then redo the timing fit and look at the residuals, they may just be white noise, which means you've got a really good model for the pulsar, but there may be some systematic trends in there, and they're the signs. Now, pulsar timing is very powerful. This just lists some of the applications of pulsar timing. I'm not going to go through all of this list, but it just illustrates to you the power. Oh, what happened there? Damn. Is that back? Yeah. It illustrates to you the power of pulsar timing. So in this talk, I'll concentrate on some of these ones up at the top, and I won't have time to go through them all. Done. Is that back? Right. Okay, so pulsar braking, I'll say a few words about that. All pulsars slow down due to energy loss, either to magnetic dipole radiation, which are electromagnetic waves at the rotation frequency of the pulsar, or to relativistic particle winds. Because the pulsars are rotation powered, they're powered by rotational kinetic energy, losing energy causes the pulsar to slow down. There are some very interesting pulsars known as intermittent pulsars, where the pulse goes into what's called a null for a certain period of time. Several months in these cases. You do get shorter nulls as well. And then it comes back on. And in this important paper by Michael Kramer in 2006, they showed that the rate of slowdown of the pulsar was different when it was pulsing and when it wasn't pulsing. And that demonstrates clearly that the same currents are responsible for both the spin down of the pulsar and the radio emission. Now you can define a parameter called the braking index, which is related to the pulse frequency, its second derivative, and the first derivative squared, which is a diagnostic of the mechanism for the pulsar braking. If it's a pure magnetic dipole effect, then this braking index is equal to 3. But if it's if the braking is largely due to stellar winds, then the braking index is less than 3. And the direct measurement of this braking index for a few young pulsars generally gives values that are somewhat less than 3. So that's consistent with the particle wind contributing to braking. Unfortunately, it's impossible to measure the braking index for millisecond pulsars. This new dot term on the bottom line here is just too small, and so it's just not possible to measure the braking index. What's happened? Very strange going on here. Can't move on. No. I'll try again. Okay. So most of you will know about glitches. These are sudden spin-ups in the pulse frequency. There have been 425 glitches observed in 141 pulsars. That's at least according to our ATNF catalogue list. The spin-up is generally between 10 to the minus 10. In fact, there could be a lot of glitches less than that. That's really an observational limit. And the biggest ones known are about 3 by 10 to the minus 5. This is for spin-powered pulsars. There's been a recent paper for an accretion-powered long-period pulsar, 1,000-second period, which has a bigger delta nu over nu than this. An important diagnostic of what's going on is the amount of change in the spin-down rate, and that's generally about 10 to the minus 3 for the larger glitches. It's hard to measure for the smaller glitches. It's found that there are typically a combination of exponential and linear decays back toward the equilibrium state. So this is an exponential initial decay here in the frequency derivative, and then it tends to be a more linear function. So in a recent paper, Espinosa and Andrew Line and others fitted a template to these exponential plus linear decays, the first part of that, and they see an increasing trend in this sort of central point of this template. And from that, they can compute a braking index, and they obtain these values, which are all considerably less than 3. And in particular for VLA, this is a VLA pulsar, they get 1.7 plus or minus 0.2. So that's unusual, or maybe unexpected, and it's maybe also a bit controversial. I was just reading today or yesterday about looking through ADS, and I came across this paper by Akbal and Ali Alpar and colleagues, where they use a somewhat different method of taking nu dot just before the glitch, and they get for VLA 2.81 plus or minus 0.12, which is very different to this, completely different, well outside the combined uncertainties. So I think there's a lot yet that we don't understand about what's going on here. This is quite a conventional value, whereas this is an unusual value. Okay, so that's all I had planned to say about glitches. I've lost track of time now that I had to restart that, so 7 minutes. Oh, gee. Okay, so I'll have to rush. So you've all heard of the Hulse-Taylor binary, so I won't dwell on that. The important point here is that by measuring 2 of these post-Keplerian parameters in GR, these are just dependent on the masses of the pulsar and the companion. So once you've measured these 2, you can compute the pulsar masses. Then you can then predict what the third relativistic effect, the orbital period decay, should be, and thereby test general relativity. And this is a well-known figure for this prediction of the orbital decay in the Hulse-Taylor binary, and GR predicts it precisely. So this was not only a confirmation of general relativity, but it was the first observational evidence for gravitational waves, because that gravitational waves is the energy loss process that causes the orbit to decay. So that's a very famous result. Just going on to the double pulsar, which we discovered at Parkes back in the early 2000s. It has an even shorter orbital period than the Hulse-Taylor one, and so these relativistic effects are even bigger. We published results in 2006 where we had a total of 5 relativistic terms. We're now updating that, and so there's a total of 6. This is the so-called mass-mass diagram, which is quite complicated and busy, but the important point here is that these various relativistic terms all imply allowed regions on this diagram. And if the theory of gravity that you use is a good one, then there should be a region on this diagram where there are 2 masses which are consistent with all of these constraints. And if this is a blow-up of this central part and there's a tiny little region there which is consistent with all the constraints. So that means general relativity is accurately describing this, this system. And we now have the best measurement of the orbital period decay, which is an order of magnitude better than the measurement in the Hulse-Taylor system now, and to 0.02%, and it's fully consistent with the GR limit. I was going to say a little bit about other tests of gravitational theories. I mean, GR is not the only theory of gravity. So in principle, you can use pulsars to place, well, not only in principle, in practice, you can limit the parameters of other theories of gravity. Since I'm running out of time, I might have to skip this. This is a pulsar triple system, and there's a talk actually this afternoon by one of Jason's students or postdoc, I'm not sure, about this system, so I won't say too much about it. The reason I put it in was that there is the potential with this system of providing a very sensitive test of the strong equivalence principle. There's an effect where if the system is in an external gravitational field, it will induce an eccentricity in the orbit, and that's usually tested by the gravitational field of the galaxy, but here you can actually test it with the gravitational field of the second outer planet, and it's potentially much more sensitive. So moving on to pulsar timing arrays. Pulsar timing arrays are arrays of millisecond pulsars which are spread across the sky. And in principle, you can detect gravitational waves and other effects with these pulsar timing arrays. We all know, of course, that gravitational waves have now been detected by LIGO. It's a fantastic result, and not only have they found this one, the first one, but there are now 3 others, which are quite surprisingly are all double black hole systems, no double neutron stars yet. But I just wanted to point out that in terms of tests of general relativity, the double pulsar is still a far better test at the low orders. There's a confusing way they labelled the post-Newtonian orders in the GW community, but this 0 term is actually the first gravitational radiation term, which goes as V upon c to the 5th, and the double pulsar test is what, nearly 4 orders of magnitude better than the test from the GWB. And even the second term, which goes as V upon c to the 6th, the double pulsar gives a better limit. After that, the GWB gives a better limit because V upon c for the double pulsar is relatively small, only 0.002, whereas it's of order 1 for the GWB. So getting back to pulsar timing arrays, we can, in principle, we can detect several different effects with these. What we're looking for is a signal in the different pulsars which is correlated between the different pulsars. So that means it's not just related to one pulsar. And we can detect clock errors. So if all of the pulsars are speeding up or slowing down together, that's not due to the pulsars themselves. It has to be due to something here on Earth. And the most likely effect is an error in your in the reference timescale. If you think of that in terms of distribution on the sky, that is a monopole signature. We use the solar system ephemeris to convert to the barycenter. If that's in error, that basically means the Earth's not where we think it is, and so pulsars over here will arrive a bit early, pulsars over here will arrive a bit late, so that's a dipole signature. And gravitational waves have a quadrupolar signature, which is illustrated by this famous Hellings and Downs curve. So in principle, we can separate all these things. There are three major pulsar timing arrays around the world: the European, North American, and the Parkes one. At the moment, we've only been able to limit the strength of a gravitational wave background at these at the very low frequencies that these pulsar timing arrays are sensitive to, in the nanohertz band. And that's disappointing in a way, but it's also quite interesting because we're now ruling out most of the standard models for the formation and evolution of galaxies and the supermassive black holes in their cores. So some of the assumptions that went into the predictions for these models, for the amplitude of the gravitational wave background, must be wrong. And it could be the black hole mass function, or it could be the merger rate, or it could be other things. We would, of course, like to detect gravitational waves with a pulsar timing array. And the best way to do that, it turns out, is to increase the number of pulsars in the array. So the first step in doing that is to form the International Pulsar Timing Array and combine the data sets from the three national or regional PTAs. So we've now done that, and we're working on those data sets. In the future, we expect China with FAST and the QTT in Xinjiang to contribute to the pulsar timing array effort, and South Africa with Meerkat, and ultimately SKA-1. So there'll be many more observations of many more pulsars. We could even have hundreds of pulsars in a PTA, and with that we think we're almost certain to detect these gravitational waves and in fact be able to study them. I'll just say a few words about the pulsar-based timescale. I mentioned that if the reference clock is irregular, then you would expect to see this effect in all of the pulsars. So that's what we're doing here. We're searching for so-called common mode signal that's affecting all of the pulsars in the same way. And so with that, we can potentially establish a pulsar timescale which is based on the pulsars. And to do that, we sort of invert the usual problem of timing the pulsars with respect to the reference clock. We turn it around and we time the reference clock with respect to the pulsars. And that defines this pulsar timescale, which is independent of Earth-based timescales. It's based on the pulsars, which are way out there. It's based on completely different physics. Atomic clocks are based on quantum mechanics. The pulsar timescale is based on rotation of a macroscopic object. And importantly, the pulsar timescale will continue for billions of years. Atomic clocks only last 10 or 20 years, and then they have to replace them. So there's potential for errors to creep in on that, but the pulsar timescale will keep going forever, basically. So this shows our latest results on this. I probably don't have time to explain it in detail, but the important point is up here, where we're timing, looking for a common signal with respect to international atomic time. Now, international atomic time is known to have errors in it, and there's an improved timescale called TTBIPM15, and this red line is the difference between those two timescales. And you can see that the pulsar timescale, which is this blue line, and also these points with error bars for two independent analysis methods, do in fact follow the difference between BIPM15 and TAI. So that's quite important, because that shows, first of all, that TTBIPM15 is a more stable timescale than international atomic time. The clock people believed that it was, but they didn't really know for sure, and we've now proved that. And it also shows that the low frequency, long-term low frequency stability of the pulsar timescale is comparable to that of the best atomic timescales. So finally, just a little bit about spacecraft navigation. Pulsars can form effectively a GPS system for navigation in space. GPS is used, everybody has it on their mobile phone, and that's based on satellites going around the Earth. But if you're in a spacecraft halfway to Mars or something, that's not much use to you. But you can, in fact, use the pulsars as beacons and solve the timing equations for the position of the spacecraft. Normally, when we're doing pulsar timing, we put in the position of the observatory, and then we solve for the pulsar parameters. But again, you can invert that problem and use the pulsar timing parameters as input and solve for the position of the observatory, which in this case would be some space probe. So China's actually launched a satellite called XPNav, which is exploring this idea. So there's a lot of interest in this. So pulsar timing has got many, many possible applications in physics and astrophysics, and it often provides quite unique results and insights into these topics. I've only just really skimmed the surface of just a few of the possibilities that you can analyze with pulsar timing. And there's lots of, or quite a few new and large radio telescopes coming online soon, so the future for pulsar timing is quite bright. I'll stop there, thank you.
Ali?
Dick, I'd like to comment on the braking indices. This recent paper we published with Onur Akbal, who's here. When you try to find the braking index, the problem is to extract internal effects of the neutron star, the response to the previous glitch. And as you pointed out, there are exponentially relaxing effects, and then there are long-term power law behavior. Now, what was done in the earlier papers was to take a fiducial time, which was a certain time, like 150 days in the case of the VLA pulsar, after the glitch, which is fine for exponential relaxation because you are sure that it's over by that time. But when you have power law behavior, as you showed there is, then you have to wait as long as possible and compare the amplitude of that term with the way it's relaxing, and then you choose a fiducial phase just before the next glitch. And when you do that, then we obtained for the VLA pulsar 2.8.
Yeah, I haven't had time to read your paper yet, but But clearly there are quite different results being obtained from these two different methods, and so it needs to be sorted out.
Matthew?
Dick, so back on the glitches again, you've highlighted three prominent cases where we have very good data monitoring, and they all show exponential with subsequent linear recovery. Do we have any sources that buck that trend, have a different type character in terms of the recovery history?
Yeah, well, there are some where these trends are not so clear. I think, often, for small glitches, you can't resolve these things. You just don't have the sensitivity. It does seem to me that most large glitches, this is a pretty characteristic sort of behavior. But the pulsar glitches, there's a whole zoo of them, and the crab, for example, is quite different. There seem to be the sort of VLA class glitches all seem to behave in this way, but other glitches, maybe smaller ones, do seem to have different properties. So it's not universal. I think it's a very complicated phenomenology on these things, but at least this characteristic exponential plus linear does seem to be quite. It's present in most of the strongly glitching pulsars.
We must move on, so let's thank again Nick. And the next speaker is Professor Andrianov, who is going to talk about the results of the RadioAstron mission.
I will say about probing of interstellar plasma distribution in the direction to pulsars 0525 and 1919 with RadioAstron mission. The RadioAstron spacecraft present a unique opportunity to measure properties of interstellar scattering. The fluctuations responsible for scattering radio waves from astronomical sources are small-scale fluctuation in electron density of interstellar medium. There are three main components of interstellar plasma, and scattering of nearby pulsars and the intraday variability of quasars point to the existence of a component of interstellar medium which has properties quite different from the more distant diffuse interstellar medium. We observe several nearby bright pulsars as part of RadioAstron science program. And in this presentation, we present results concerning distribution and properties of scattering in direction to pulsars 1919 and the pulsar 0525. Scattering causes angle broadening, pulse broadening, intensity modulation or scintillation, and distortion of radio spectra. Scattering involves a signal emitted at the source with an impulse response function reflecting a reinforcement on cancellation of radiation from different paths with different optical lengths. On this picture you can see a dynamic spectrum of pulsar 1919, and you can see spots of bright and low intensity dynamic spectrum. Relative length of different bands change with observed position, so the impulse response function changes with position too. For most sources and wavelengths of interest, the lateral scale of the change is greater than the diameter of Earth. However, in many interesting cases, it's smaller than the distance between Earth and Space Radio Telescope radiostron. Thus, only radioastron with ground antennas can simultaneously observe the impulse response function in two different locations, in two different diffractive spots. Radioastron is a space ground interferometer with maximum baseline projection up to 350,000 kilometers. Radioastron works with 4 frequency band. For pulsar observations, we use only first 2 bands. Radioastron was launched 18 July 2011. Observations of Pulsar 1919 was performed at 4 July 2012, and with the baseline projection is about 60,000 kilometers. Total time duration of our observation is about 1 hour, and we use space telescope radioastron and big ground telescopes in Green Bank and Westerbork. Data were processed with IC correlator, with dispersion and gating. And the IC correlator produced complex cross spectra, dynamic spectra of pulsar. On this figure, you can see dynamic spectrum of pulsar 1919, and on this picture, you can see several individual pulses. You can see 2 frequency scales in individual pulses, an arrow about 400 kHz and white about 1.5 megahertz. Slope in the dynamic spectrum show presence of refraction or cosmic prism, and we have modulation index about 1 this pulsar, and it corresponds to strong scattering regime. For analysis data, we can define cross-correlation function from dynamic spectrum, and we determine cross-correlation function for ground as space ground baselines different ways due to we have poor interferometric phase on ground baseline due to ionospheric effect, and we have good signal to noise ratio on ground baseline, and on space ground baseline we have good phase but poor signal to noise ratio. You can say break in KKF on ground baseline that indicates to scale structure, and we have no break on space ground baseline that indicates absence of wide scale structure at large baselines. From covariance function we can determine frequency and time scales of scintillation, and we have a regime of strong scintillation for this pulsar, and in this regime our covariance function consists from 2 independent parts that depends only from frequency and only from baseline, and from ratio of value of this correlation function with a big frequency shift and from value in 0. We can determine a part of covariance function that depends from baseline. Next analysis we can make with the structure function. On this figure you can see structure function for ground and space ground baselines. and structure function with different time shifts. You can see that short baseline compares narrow band component and broad bandwidth component. The long baseline displays only a narrow frequency scale. For space ground baseline, a time shift of structure function produces only a decrease in amplitude of structure function without displacement of its minimum. This is consistent with the absence of white structure on the longer baseline. Two frequency scales about 300 kHz and 2 MHz corresponds to two effective layers of turbulent plasma separated in space. And shift of minimum of structure function with increasing time shift is due to refraction shift of diffraction pattern, the presence of prism in light of slide. From a value of cross-correlation function on space ground baseline, we can obtain distance to far screen and scattering angle on far screen. In observer plane, angle will be less due to geometry. From shift of minimum of structure function with maximum time separation, we find Fresnel scales for near screen, and we can determine distance to near screen. We can see that the very close to Earth. And provided that reference displacement is small, that scale of diffraction pattern, it's possible to estimate the distance to prism in distance less than 2 parsecs. Structure slope of structure function can determine the parallel index of spectrum of these heterogeneity. And we have index near the Kolmogorov one for this pulsar. So we found for the first time that the two scattering regimes realized in the direction of pulsar 99, diffraction oscillation from Gravitations in layer of turbulent plasma at a distance about 440 parsecs from observer, and weak cancellation from screen located very close to Earth. We measured scattering angle in direction to pulsar 99, and also found prism with the distance less than 2 parsecs exists in this direction. And we have parallel of index of spectral densities near Kolmogorov one. More details about analysis of pulsar 99 you can find in our article in monthly notice. Also we presented here results about pulsars 0525. We have observation in 20,000 with a projection baseline about 260 kilometers. We use telescopes Radio Estron, Green Bank, and Arecibo telescope, and Kalyazin. But data from Kalyazin telescope can be used due to strong hindrances in spectra. We use IC correlator for processing this data. And we make a similar analysis for this pulsar like analysis pulsar 99. On this slide you can see strong pulse-to-pulse variation of pulsar emission with modulation index. This corresponds to strong cancellation. On this slide you can see two individual spectra with this pulsar. And this is a congruence function for ground and space ground baseline. We use the same analysis of congruence function. We found frequency and time scales of cancellation. and from shape of structure function, we can find parallel index of spectral combinations that near to Kolmogorov. And from cross-correlation function with big frequency shift and value without shift, we can determine spatial part of cross-correlation function, and from this we can estimate spatial scale of scintillations and determine the scattering angle. You can see that our spatial scale much more that scale associated with velocity of pulsar, and this means that medium is not homogeneous, and the center of mass of our medium is shifted to pulsar. And with a model of one single screen, we can estimate the distance to the screen, and you can find that we have screen at distance about 160 parsecs from pulsars. Analysis of time and frequency structure function allowed to conclude that scintillation at frequency 1600 MHz is strong, and the diffraction of scintillation model realized. Characteristic time and frequency scales of scintillation were determined, and it shows that spectrum of homogeneous plasma is power law spectrum with a power law index near to Kolmogorov one. Scattering angle in the direction to pulsar we determine, and we show that the scattering of emission from pulsars 0525 takes place on the screen located close to pulsar, and you can see more details about this analysis in the paper in Astronomy Reports. Thanks for your attention.
Question or comments? George?
What could be the nature of these screens? And generally, what can we infer? Say you measured some properties, mostly distances, to screen, prism, and whatever. What is this physically? Excuse me, are there any correlations, say, with the screens, of the screens with other astrophysical informations, like you know, in absorption in that direction or whatever?
It's first works about distribution of interstellar plasma in direction of this pulsar. So now we can't associate this structure with some physical structures, but we have near screen in very close to Earth, and it can be associated with local bubble, for example, maybe. No, we have one screen very close to Earth, maybe in local bubble, and another screen maybe spiral AM. We have not enough information to associate with physical structure. No,
Okay. Last question by Jason.
So these are very challenging observations, but so for 1919, you fit two screens and a prism. Are there plans or data already in hand at different baselines of radio astron to try and confirm this and further constrain this interpretation? Because with different baselines, you can probe different scales of the screen. Right?
We have measurements for small baselines, ground baselines, and one big baseline. And with comparison, we have seen some structure some scales on ground baseline, and we see different structures on big, longer baseline. And with it gives us possibility to obtain a ratio of these structures.
Okay, yes, it is indeed coffee time now, so let's thank again all the speakers. Morning.
Mic check. Cool. 2, 3.
Раз, два, три. Раз, два, три.
All right, we're running a bit late. We are starting the next session. Klim Mikhailov will start with the first talk on radio frequency studies of the pulsar binary. Please.
Good afternoon, everyone. I'm Klim. I do my PhD under supervision of Yuri van Deuven at Anton Pannekoek Institute for Astronomy, which is located at the University of Amsterdam, and also at ASTRON, which is the Netherlands Institute for Radio Astronomy. Today, I would like to give an update on the collaborated multi-frequency radio and optical observations of the specific radio pulsar binary, J1614-2318. I'll outline 13 years of observation of this binary, dive more into the pulse profile studies, and then show what we currently think about the binary evolution. To begin with, there are different classes of spinning neutron stars or pulsars with the different spin periods and spin downs. These different classes are normally represented on the standard PP dot diagram that further separates them in terms of characteristic age, magnetic field strength, or spin down energy. We see that, for instance, long period normal pulses appear next to the center of the diagram, and then they move downwards due to the spin down and magnetic field decay until they reach the so-called death line, so that they cease their radio emission. On the lower left end of the diagram, we see short period millisecond pulses that are normally found in binary systems, and they can spin up due to the accretion and gaining the matter or angular momentum from their binary companions. They are normally old pulsars with moderate magnetic fields of 10 to the 8, 10 to the 9 Gauss, because the accretion causes the decay of magnetic field. There are also rotating radio transients that appear next to normal pulses, but they are generally brighter, and they emit only sporadically, so that they are normally found via single pulse searches and not periodic searches. And on the other extreme, there are also magnetars on top of this diagram that have very strong magnetic fields of 10 to the 14, 10 to the 15 Gauss, so that their radiation is caused by the magnetic field decay. We'll hear more about these objects later today. I'll focus more on millisecond pulsars. As I said, millisecond pulsars, they are bind in binary systems with their companions, such that they undergo a period of matter transfer from them. They're normally found in global clusters, such that the crowded environment in this cluster can help them gain their companion more easily. But on the other hand, the strong gravitational potential of the global cluster doesn't normally allow us to measure the intrinsic pulsar spin down and therefore its magnetic field. Nowadays, there are more than 350 millisecond pulsars known, and the fastest millisecond pulsars, they can reach, they can spin up to the point when their spin down energy can be similar to the young pulsars and therefore allow them to emit also in gamma ray, and therefore these millisecond pulsars can be also radio counterparts to the unidentified gamma ray sources, for instance those found with the EGRET telescope on Compton Gamma Ray Observatory. And one of them was the radio pulsar J1614, which was unexpectedly found via the Parkes survey of 56 mid-latitude EGRET gamma ray error boxes by unexpectedly, I'll come to this point later, but this survey was made at L band at 1.4 gigahertz and used the single 4-pointing tessellation pattern that covered 95% confidence region of each of the EGRET error box. It covered also in total 140 square degrees of the sky at moderate galactic scales about above 5 degrees. After the discovery, there was a follow-up with multiple different telescopes, such as Parkes telescope, Green Bank, Westerbork, and also low frequency rate. They spanned for almost 13 years and covered a huge frequency range from 150 megahertz up to 2 gigahertz. There were also timing observations made on a roughly monthly basis for Green Bank and Westerbork, and they ended up in sufficient amount of times of arrival, TOAs, for a timing solution. Here are the pulse profiles. They were made at different frequencies from different telescopes. The procedure of making these pulses is standard. We apply fast Fourier transform to the recorded dispersed data and then stack every single pulse on top of each other to get the highest signal to noise. We see that the profiles get more noisy towards the higher frequencies, whereas at lower frequencies there is a more detailed structure shown. And what's more interesting for low frequency profiles, especially for 350 megahertz GBT and Westerbork profiles, we see that there are additional wings next to the main pulse, therefore increasing the pulse width to almost 60-90%. And this can also imply the presence of conglomerated conal emissions, so that different beam components, I'll come to this point later. But first, in particular for Westerbork observations, we see that at different bands, at L band, 1.4 gigahertz, the pulse profile is much more dim, which results in almost 3 times less signal-to-noise ratio to that of B band, 350 megahertz, given 2 times broader bandwidth, but 3 times shorter observation time. And this can mean that the spectral index and the the spectral law is steep, so that we should expect a higher flux density at lower frequencies, which was one of the key points to try and observe this pulse at even lower frequencies with the LOFAR. A few words about polarization studies. In general, polarization can get a feeling of a Faraday rotation and interstellar scattering from the interstellar medium that the pulsar beam has to travel through in order to be captured by the radio telescope. It can also give a better estimate on the binary system angle, that is the angle between magnetic axis and rotation axis. Therefore, later observations with all these telescopes were made in full stocks regime to try and obtain polarization profile of the pulsar. Even though past Parkes and GBT observations didn't really made a success in getting the polarization due to the technical difficulties, with Westerbork we were able to sum 15 hours of observation at 350 megahertz and get 90 sigma signal-to-noise ratio. However, the polarization was quite monotonic, around zero flux, and thus we think that the pulsar should be really weakly polarized. Again, as I said, since most pulsars have steeper spectra and they have higher flux densities towards lower frequencies, they normally peak at around 150 megahertz, which is the central frequency of LOFAR high-band antennas. That's why we tried to observe this with LOFAR. We did 3 2-hour observational sessions with around 100 megahertz bandwidth and 150 microsecond sampling time. We will not be able to detect LOFAR, the pulsar with LOFAR, but set the limit on the sensitivity to about 0.1 millijanskis. Possible reasons for the non-detection can be extremely low declination for this pulsar according to the LOFAR, the angle, but also this can be pulsars intrinsically low brightness. And the scattering was estimated to give only 5% for the pulse broadening. Back to the beam components, as I said, since low frequency profiles have additional wings next to the main pulse, we think that there might be 2 different beam components present for this pulsar, which correspond to a different region of the pulsar magnetosphere, and they depend on the observational frequency. Normally, they are described by the pulse width, normally 10% and 50% level of the main peak of the pulse. That is this width. So what we did, we tried to see whether this pulsar appears on the width towards the period relation. We also used known measured pulse width from other pulsars with the separated known beam components. We estimated errors from the low frequency profiles for our pulsar. We also used the low boundary line. That basically means that there shouldn't be any pulse profile structure resolved below this line. And we consider the pulse width ratio because both widths strongly depend on the observational frequency that scaled them in the same manner. And that's why for the ratio, it shouldn't be much of the dependence. And we see that our pulsar also appears above this low boundary line that is consistent with these predictions, which means that this holds not only for core components but also for conal components, exactly in the same manner, which means that both components can indeed be present for our pulsar. Now, to further study, to better determine the binary parameters, we also observe the position of the pulsar in optical with the 4.1 meter aperture Southern Astrophysical Research Telescope at Airband. We did 15 exposures of 1 minute with a 0.8 arcsecond seeing. We didn't see the counterpart down to 25th magnitude 5 sigma significance, which is pretty deep. We also estimate the extinction, which is not really significant, is below 0.5 magnitude, and shouldn't really affect the non-detection of the counterpart. And because there was an absence of a counterpart in the solar field of view, we think that this might imply that the companion is old and called Helium white dwarf star, which is also consistent with the evolutionary models of helium white dwarf and also with the other known pulsar binaries with the helium white dwarf companions. Here's the timing solution. We obtain times of arrivals from all but lower observations. Then we combine all of them and feed for pulsar position and binary motion. The timing parameters are inconsistent with the discovery paper. And from the pulse ephemeris, we found the eccentricity to be around 0, which means almost circular orbit. We couldn't determine the binary motion. It was not really significant in our measurements. And also, we couldn't measure the Shapiro delay, which might mean that the orbit is more at the lower inclination or towards the face-on position. So for the properties of the pulsar, the pulse period is quite long. It's at around 30 milliseconds. The spin down is typical for millisecond pulsars. The characteristic age is around 10 gigayears, which is also typical. The orbital period is 3 days, and dispersion measure is around 50 parsecs per cubic centimeter, which applies 2 or 3 kiloparsecs according to different electron density model. This is the position of the pulsar on a PP dot diagram. We see that the pulsar stands a bit aside from the main bulk of the MSP population, and that is probably possible because of the extended pulse period. The magnetic field is also quite typical and consistent with the pure dipole radiation for the MSP population. At the same time, it also means that the companion was not really able to fully recycle the pulsar. The spin down energy is quite low and therefore is not sufficient for the pulsar to emit in a gamma ray. And this is indeed the reason why the pulsar was found unexpectedly. So it's not associated with any of egret sources. And what's more interesting, the minimum companion mass is really small compared to the pulsar spin period, which makes this the second lowest minimum companion mass for partially recycled pulsars with the spin periods between 10 and 100 milliseconds. The record holder, the first smallest minimum companion mass belongs to the similar pulsar binary that was found during the high time resolution survey with Parkes. It has also similar pulse period, very small minimum companion mass, and also other characteristics which is pretty similar to our binary. And that implies that for these both pulsars, there might be a different evolutionary scenario of the binary. And speaking of binary evolution scenarios, here we plot the dependence of a binary orbital period versus the medium companion mass at a 60 degrees inclination. We also show the theoretical correlation between these two parameters given different progenitor metallicities. And we also put other pulsar binaries with well-measured masses, and our pulsar is shown here. The spin period is shown in parentheses. And if we apply error bars on the mass given Shapiro delay measurements, and for those that don't have these measurements, we apply uniform distribution of orbital orientations, then these error bars can also move forward and therefore fit this theoretical relation, which means that in this case, the orbital inclination can be really small and the companion mass can be indeed more heavier. But in this case, then, it's the randomly oriented orbit is very unlikely. It's only 8% probability of getting this rare inclination. However, in this case, there is almost no influence on the pulsar from a companion, such as eclipses, and therefore the only estimate we can get for the mass is from Kepler laws. And this can explain why the mass of the companion is so underestimated. We're unable to measure Shapiro delay and therefore not able to measure post-Keplerian parameters, such that leads to direct estimated masses. In this case, one more puzzle is why there is a relatively long spin period, because if the pulsar binary undergoes a period of mass accretion, what can also be is that the magnetic field should inhibit the process of accretion so that the pulsar cannot be easily spun up. Therefore, we think that there might be an inefficient accretion onto the pulsar such that the the magnetic field can be initially weak and then still ends up to be normal, typical for pulsars as 10 to the 9 Gauss. However, the accretion channel may be relatively weak such that the pulsar is not really spun up because of that. Other possible scenarios can be that there might be different formation scenario. For instance, as if the oxygen neomagnesium white dwarf can turn into the neutron star under the accretion-induced collapse. However, this applies only when the orbital period of the binary is really long and from 10 to 60 days, which is not the case. That's why we think it's not really a plausible scenario for our case. And also there can be both different mass and composition of the binary, such that with the carbon helium white dwarfs, we know that many pulsars with such type of companions can be partially recycled. In this case, the mass should be lower, the mass should be higher, and the evolutionary scenario can be completely different from those I showed earlier. To sum up, this is an overview of the 13-year campaign of radio observation and timing of this particular binary. We saw that the spin energy is not high enough to produce gamma ray emission. That's why the pulsar was found unexpectedly. We saw additional wings that results in an increase of pulse duty cycle, which means the presence of additional beam components, and also that the evidence that we have almost 90% coverage of radio beam means that the magnetic axis can be nearly aligned with the rotational axis. And at the same time, if the companion mass is heavier and the orbit is at low inclination and face on, then the orbital line can also be nearly aligned with the magnetic axis and rotational axis. That's why we have 3 nearly aligned lines, and therefore we might deal with the rare case of a nearly aligned rotator. And of course, the discovery of more such alike pulse binaries can shed more light on the evolution of such binaries, as well as accretion efficiency of these binaries. Thank you.
Thank you very much, Klim. Are there questions? Dick?
So can you really rule out a more massive companion? At this 0.022 number, is that the sort of the mean or the median value that you expect? If you've got a almost aligned system, almost face-on system,
yep.
Could the companion mass be much larger?
Yeah, I think because we can't really constrain the mass because of the face-on orbit. The mass can be heavier, and we also saw from the evolutionary scenario that if it can fit the theoretical prediction, then it should be heavier.
But you don't think a double neutron star system is possible?
But then it should be much heavier. It's not prohibited, so yeah.
Are there more questions? If not, let's then thank the speaker again. Okay, the next talk will be given by Kusinskaya, Conquering Systematics in the Timing of the Pulsar Triple System.
Yeah. Hello everyone, my name is Nina. I'm a PhD student in the University of Amsterdam, and I'm working with Jason Hessels and with his postdoc Anna Archibald. We working on the very unique, the only pulsar in a stellar triple system, J0 337 plus 1715. And we trying to conquer the systematics in the data of this pulsar to test equivalence principle of Einstein.